Hi everyone. In this module we're going to talk about determinants and learn a ton of things about them. They are kind of magic numbers that can tell us so many different things about different situations where we have some square matrix that's playing a role. So we're going to start by learning how to compute the numbers, and then we're going to see some applications, and then we are going to see some magic tricks that will allow us to use determinants to compute the inverse of a matrix, and we'll also be able to use determinants in a really clever way to solve a linear system, and that is Cramer's rule. So let's get started with part 1 about how to compute the determinant of small matrices, that is 2 by 2 and 3 by 3 matrices. Okay, first of all, the determinant of a matrix is just a scalar value that can be computed from the entries in the matrix. And every square matrix has a determinant, and only square matrices have determinants. Now, computing the determinant of a matrix can look a little bit arbitrary, but computing the determinant of at least a 1 by 1 matrix is super easy. So if we have a 1 by 1 matrix A that just has a single entry, so 1 row, 1 column, the determinant of that matrix, which we write like this, is just equal to that entry, whatever it is. Since we're working in such an easy case, I think I'll take the time to show you some of the notations for determinants. So I could also write the determinant of A like this. Another way people like to write determinants is using absolute value signs. The determinant of A is equal to, in this case, A, because it's a 1 by 1. And I usually find myself mostly using this one. And I think that's what our text mostly uses too. And occasionally this one. Okay, so that's how to compute the determinant of a 1 by 1 matrix. No problem at all. Let's see how to compute the determinant of a 2 by 2 matrix. Let's look at our generic favorite 2 by 2 matrix, ABCD, and I'll tell you how to compute the determinant of it. So here, the determinant of A is equal to A times D minus B times C. For example, if we want to compute the determinant, let's say we have matrix B, 2, 1, minus 3, 4. The determinant of B, which I could also write this way, this is going to be 8 minus a negative 3. So that's equal to 11. That's the value of the determinant of that matrix. Now this value is something that you've seen before. It's for the computation of the inverse of a 2 by 2 matrix is where that appears. So if we have our matrix A equal to ABCD, then A inverse, right, we had this formula for that. It was 1 over AD minus BC. And then we remember we swap the diagonal entries and negate the off-diagonal entries. This quantity now is just what we've been talking about. This is the determinant of A. So we'll often see this formula written down as 1 over det A, and then we have this dA minus B minus C. Okay, so that's the determinant of a 2 by 2, and we can see where it's arisen before. Let's see next what we can do with that. Well, there are a couple of things right away that we can see that the determinant will tell us about. We know that if the determinant of a matrix is equal to 0 for a 2 by 2 matrix, that inverse can't exist, because A inverse is equal to 1 over det A times that other mixed up matrix. And we know that we can't divide by 0. So if the determinant of our matrix is equal to 0, then we know that A inverse doesn't exist. And knowing that A inverse doesn't exist tells us something about the solutions to the linear system that has A as its coefficient matrix. So let's just remember that what we mean there is we're talking about a linear system that looks like AX equals B. And if A inverse doesn't exist, then what do we know about the solution set for the system of equations? Well, we know that there might be no solutions, or it might have infinitely many solutions. And that's because if A inverse did exist, then we could just multiply A inverse times B and get our unique solution like we did 2 modules back. Now, one other thing we can use it for that's kind of nifty is finding the area of a parallelogram. So let's start simple. So here I have two just generic vectors in 2 dimensions, and I want to look at a special case here where the second component of the u vector is 0, and the first component of the v vector is 0. Let's make a picture of this. Okay, so I have my u vector oriented along the horizontal axis, and that's because the y component, right, of that vector, the vertical component of that vector is 0, and similarly with the v vector, right, that's oriented along the vertical axis. Now, what's the parallelogram that's determined by these 2 vectors? Well, to find that, I'll just take a copy of the u vector and situate it so that its tail is right at the tip of that v vector. And same with the v vector. Now, this area in here, this is a rectangle. The width is u1, and the height is v2. And that's the area of our rectangle. Now let's compare that to the determinant of a particular matrix. I'm going to take the matrix that has as its columns precisely these 2 vectors. And if I compute the determinant of that 2 by 2 matrix, that is u1 times v2, which happens to be exactly the area that we found when we computed it directly from the diagram. And so that's one really kind of trivial case. Let's move on to something a little bit more sophisticated. With these vectors, I have essentially the same genericity as I had in the first case. The only difference is now that this first component of the v vector is allowed to be non-zero. So let's draw a picture. And now if we take a second to look at this, we see that our v vector sits out here. It's got 2 components that can be non-zero, and I've marked them off on the axes. So the first component, v1, would be somewhere here. The second component, v2, is somewhere over here. We have these 2 vectors. Now let's see what is going to be the parallelogram that's determined by these 2 vectors. And what is its area? Well, if you remember the formula for the area of a parallelogram, that's great. It's just the base times the height. Now if you're a little hazy on that formula, you can imagine taking this triangle that's sticking off on this side and just picking it up and moving it over here. Those 2 triangles are congruent, and then if we cut and paste like that, then what we'll end up with is a rectangle that has precisely the area that that parallelogram did. Anyway, to figure out the area of this parallelogram, we can just plug in. So that is our area. Now if I set up the same kind of situation where I make this matrix that has as its columns these 2 vectors and then take its determinant, I'll get this. So I have u1, 0, v1, v2, and the determinant of this quantity is u1 times v2 minus v1 times 0. And it's again u1, v2. That is exactly what we got over here for the area when we computed it directly from the diagram. This works in the general case as well, where u2 doesn't have to be 0, right? Where all of these values are allowed to be whatever they want. I'm not going to go through the proof of that, but I can show you a picture. And now let's just do an example where we have 2 non-zero vectors. So let's take vector u to be equal to -1, 4, and vector v to be equal to 2, 2. We can draw the picture of these 2 vectors. And now we can draw a picture of the parallelogram determined by them. So now what's the area of this? Well, I certainly don't want to try and find it using geometry, but I will try to find it using linear algebra. I'll take the determinant of the matrix that has first column -1, 4 and second column 2, 2. And if I compute this determinant, I will get -10. So that's a little bit wonky, right? Because we have now a negative area. But what does that mean? Well, it's sort of like, you remember in calculus when if you integrate and you find an area, sometimes you have to take the absolute value of it if it's below the horizontal axis. Well, it's the same situation here. It's all about orientation. In this case, we're taking the area, you can kind of think of it as sweeping from the first column vector over to the second column vector. And you'll notice that that's backwards from what we did here. Here we swept from the first column vector around counterclockwise to the second column vector. So in this case, it's just like having a region under the horizontal axis when you're taking an integral to find an area. And we just need to take the absolute value of this. If I had swapped these columns, I would get positive 10 as the determinant. Now I think it's worth writing down a theorem. So now we know how to find the determinant of a 2 by 2 matrix. In the next video, we'll see how to compute the determinant of a 3 by 3 matrix.